The previous session provided the proof for the law of reflection on the basis of wave theory. This session we shall discuss the proof for the law of refraction by wave theory. There are two diagrams. One is ray optics, other is wave optics. In ray optics, you are considering only one ray of light traveling in space. Let me recall the law of refraction. It is known as Snell's law. Give the definition for this. When the light is traveling from one medium to other medium, let us say medium 1 is rarer medium, medium 2 is denser medium. Less optical density, more optical density. You are feeling refractive index of medium 1, refractive index of medium 2. And there is always the velocity difference when the light is traveling. V1 is velocity in the rarer medium, V2 is the velocity in the denser medium, where V2 is little less than V1. In this case, the line is called as incident ray, and this line is called normal. It is perpendicular to the surface at this point. The angle between this line is called as I, angle of incidence, and the angle between this line and this line, normal, and this is the refracted ray, is angle of refraction. So it is getting deviated towards normal while traveling from rarer to denser medium, or R is less than I. If we take the ratio of these two angles as a function of trigonometry as sin I by sin R, it is equals to V1 by V2 or N2 by N1. In accordance with the Snell's law, this ratio is always constant. This constant ratio is equals to either V1 by V2 or N2 by N1. You have to prove this. This is Snell's law. We can prove this is sin I by sin R equals V1 by U2, V1 by V2. That is the velocity of light in medium 1, velocity of light in medium 2. This is a geometry we are considering. Just like in the previous class, we are considering two parallel rays enclosing plane of wavefronts in series. They are generated in series and traveling in succession like this. This is the geometry before incidence, and this is the geometry after refraction, that is passing from one medium to other medium. Refracted wavefront and incident wavefront. In this series of wavefront is traveling like this in this angle alignment. This is the wavefront. It is called as incident wavefront. That is, when make an incident here, this point is in touch with the surface, but this point is away from the surface. Still, this is known as incident wavefront. After the refraction here from this point here, bending. So at this point, these are again plane here, and this is called as a refracted wavefront. Here touching here and here. From here is gap like this and generated like this. So is incident wavefront that is just touching the surface, and it is a refracted wavefront just appear after the refraction, the plane. And in this case, this angle between this line and this line, this plane and this plane, there is a plane of surface, there is a wavefront, is I, because we can calculate using this. As you know, this is a incident ray, you can consider this is a normal. This is always I. and the angle between this ray and this line is always perpendicular, because this is always perpendicular. This is 90 degree. If this is 90 degree, this angle is 90 minus I. And here angle between this line and this line is 90. If this is 90 minus I, this must be I. So like that, we can calculate I like this. Similarly, we can calculate the angle between this plane and this plane is R, using this geometry like this. So this is angle I is angle of incidence. That is angle between the incident wavefront and the surface of refraction. And R is the angle between the refracted wavefront and the surface of refraction, R. So using this geometry, you have to prove this is sin I by sin R equals V1 by V2. We shall go for proof. This same geometry I am considering here, taking only incident wavefront and refracted wavefront, and concentrate on this incident wavefront. Here incident wavefront is perpendicular to these two lines. When making a touch as incident on the surface, this point is in touch with the surface, but this point is away from the surface like this, at a distance like this. Up to this, the wavefront is planar after touching, but from this point to this point, the light is traveling. How does it travel? In the form of wavefront. So the wavefronts are spherical in shape. So wavefronts are generated spherical in shape from this point to this point. The spherical shape, that is, these wavefronts are converging spherical wavefronts, converging to this point. Wavefronts are converging to this point, converging wavefronts. That is the shape of the wavefront. And from this surface, the light after refraction, here the plane wave, that is plane wavefront arises from this point. The plane between this point and this point, then planes are generated. What about the light while traveling from this point to this point in the second medium? It is bending like this. Again, spherical wavefronts. The spherical wavefronts, that is diverging wavefronts from this point. Here, spherical again, but diverging from this point. Here, spherical wavefronts converging to these points. The difference. Wavefronts are converged to point, wavefronts are diverging away from this point like this. This is how the light travels from this point to this point and this point to this point. Here remaining are planar wavefronts. And this incident wavefront, now you can see that it is what is that? It's a tangent, a plane of tangent. It is a plane of tangent to this sphere, this spherical wavefront. Plane of tangent to this sphere passing through the point C and A. That should be understood. What is the incident wavefront in this geometry? It is a plane of tangent to this sphere passing through point C and A. What is this refracted wavefront? It is similar to this one. It is a plane of tangent to this sphere passing through point D and B. The difference. So plane of wavefronts commencing here, ending plane of wavefronts here commencing. It is plane of wavefront tangent to this sphere. It is a plane of wavefront tangent to this sphere between these 2 points, between these 2 points. That is the geometry you need to understand. While the light is traveling from one medium to other medium, refracting through one medium to other medium. In this geometry of drawing, there appears 2 triangles. We can ABC is one triangle, it is a right angle triangle because angle between this line is 90 degree. This plane is always perpendicular to ray. And one more triangle, that is ABD, again right angle triangle. ABC and ABD, two triangles, right angle triangles appear. And this AB is a common side for both the triangles, and also hypotenuse, that is a common hypotenuse for both the triangles. It is hypotenuse for both this triangle as well as this triangle. This angle is 90 degree, 90 degree. Now consider these two triangles for the proving Snell's law. This triangle, let us apply sine of this angle. For this angle, opposite side is this, hypotenuse side is this. For this angle, opposite side is this, hypotenuse side is this. Apply sine I. Sine I equals BC by AB, opposite by hypotenuse. Sine R equals opposite by hypotenuse. AD by AB, this triangle. And take the ratio of these trigonometric functions, sin I by sin R, and you have to divide this by this, where AB is common, get cancelled. Same remaining is BC by AD. What is DC in this diagram? DC is your C to B. It is the distance travelled by light from this point to this point. What is AD? AD is the distance travelled by the light after refraction from A to B. The interesting point is this. The time taken by the light to travel from this point to this point is same as the pointer traveled from this point to this point. This distance is smaller, this distance is higher, little higher, because more velocity, less velocity. That is a distance. So T, we can calculate this distance of light in terms of velocity of light and time taken. That T is the time taken for the light to travel from this point to this point, as well as this point to this point. Both are same. Time is same for both. And the distance is called as velocity into time. You can write distance as velocity into time. This velocity is v1, this velocity is v2. In this medium, velocity is v2. So this into this gives distance, this distance AD. So in this sin A by sin R, the ratio is U. What is that? Rewrite this, substitute that, replace of this ratio by this ratio. That is v1 by t divided by v2 by t. The final equation where t same get cancelled, remaining is v1 by v2. Look at this. This equation is same as this equation. The sin A by sin R equals v1 by v2. This is how we can prove the Snell's law based on wave theory. That is a proof for wave geometry. We do require again geometry, that is knowledge of geometry for the proof. It is true. Thank you.